Section 3.3, Day 2, Linear Programming. So first of all, we got to get through some vocabulary. We have to understand what linear programming is. Linear programming is the process of optimizing a linear objective function subject to a system of linear inequalities. So what this basically means is if we're optimizing something, we're going to be finding an optimum. In other words, a maximum or a minimum. We're going to be given a linear objective function. And in order to be able to evaluate that, we're also going to be graphing a system of linear inequalities. So now let's define what some of these things are in this definition. The objective function is the function being optimized. In other words, typically it's going to be a profit function, so it's also known as a profit function. So if we sell something for $35 and we sell something for $38, how many of each do we need to make, given some constraints, to maximize our profit? So then we have our constraints. And our constraints are the linear inequalities that form the system. And so they're constraining and making a feasible region, which is the bounded region formed after graphing the constraints. So basically we're generally, not always, but generally going to be given a closed region after we graph our inequalities, and then we're going to optimize it. Optimization is the finding of the maximum or minimum value of some variable quantity. And they've found that the vertices of the feasible region, so this closed region that we're going to be graphing, the vertices of that, the corners, are going to be the optimizers. Those are going to be the values that we're going to plug into our objective function. And so a lot of this is going to make a lot more sense once we actually do some problems. So that's the vocabulary. And so now let's get down to do some problems. So we're going to find the minimum and maximum values of the objective function subject to the given restraints. So c equals 6x minus 2y. We're not graphing that. We're not given what it's equal to, so we actually couldn't graph that even if we wanted to, because we would have no way of finding an x or y intercept. This is our objective function. So we're going to leave that alone until we get our linear inequalities graphed. And so all these inequalities, all these equations with inequality systems or inequality signs in them, are what we need to graph. So to begin with, we're going to solve the first one for y so we can graph it. Y is less than or equal to negative x plus 9. So as we go through this, I would encourage you to pause the video and solve them and graph them on your own, and then come back to see if we match. So when we graph this first inequality, we're going to get this graph. Solving the next one for y, y is greater than or equal to negative 4x plus 12. So again, please pause the video and go ahead and graph these. And you'll get this graph. It's graphed to the right. And then x is greater than or equal to 0 is just going to be that vertical line, constraining it to the first quadrant. And y is greater than or equal to 0. So again, it's constraining it to the first quadrant. And now this looks kind of messy, so let's go ahead and figure out where all these regions overlap. And when we look at where all the lines cross, this orange section is the feasible region. That's the area that we've graphed in. And now the vertices of this. So the first vertex is at 3, 0. And I think I'm just going around counterclockwise. The next one would be 9, 0 over on the x-axis. And then 1, 8. And so now what we're going to do with these is now is when we're going to use this objective function. And so we have these ordered pairs, x and y, and we're going to be plugging those in for the x and the y in our objective function. So plugging in the 3 and the 0 for x and y, we're going to get 18 minus 0, so we get a value of 18. We're going to do this for all of the vertices. So again, plugging in 9 and 0, 54 minus 0 gives us 54. And then again, plugging in 1 and 8 for the x and the y, we're going to get 6 minus 16, and so we're going to get negative 10. And so now looking at these values, the biggest value is 54, and the smallest value is negative 10. So therefore we have a max of 54 at 9, 0, and a min, or minimum value, of negative 10 at the ordered pair 1, 8. And this is our solution. Let's go ahead and do another example. Again, we're going to ignore this objective function for a minute, and the first thing that we need to do is graph our inequalities. So solving the first one for y, we get y is less than or equal to negative x plus 5. So we're going to graph that. And then we have x is greater than 1, so that's going to be a vertical line shaded to the right. And y is greater than 2, so that's going to be a horizontal line shaded above. And then again in a different color, or at least darker if you're just using your pencil, we need to figure out where exactly these lines cross and what our shaded region is, our feasible region. And so now that we've done that, we can determine that our vertices are at 1, 2, 3, 2, and 1, 4. And again, the next thing we do now is when we go ahead and we use that objective function, and we plug the 1 in for the x and the 2 in for the y. We get a value of 7. Plugging in the 3 for the x and the 2 for the y, we get a value of 9. And plugging in 1 and 4, we get a value of 13. So again, we can see what our smallest and our biggest value is. So we have a minimum value of 7 at the ordered pair 1, 2, and a maximum value of 13 at the ordered pair 1, 4. And so this would be our solution if we're just given a math problem to do. Now we're going to go ahead and take a look at a word problem. But if there's any part of these last two problems that you don't understand, and I understand that this can be very confusing, please make sure you highlight that or put a star by it and you come into class and ask some questions on it. Or if it helps, you might also want to rewind and go through one or both of these examples a little bit slower now that you've watched them once to see if you can understand what we're doing. So now we're going to deal with a word problem. Potter wants to make and sell serving bowls and plates. A bowl uses 5 pounds of clay and a plate uses 4 pounds of clay. The potter has 40 pounds of clay and wants to make at least 4 bowls. How many bowls and plates should he make to maximize his profit if the bowls profit $35 and the plates profit $30? So the first thing we need to do is define our variables. And where do we look to define our variables? You always look in the question. So the question asks us how many bowls and plates. Therefore, our variables need to be defined as x is the number of bowls and y is the number of plates. Next, we've got our profit or objective function. So if we're thinking about what we're trying to maximize, that's what our profit or objective function is always going to do. You're going to look for the word maximize, or sometimes we might want to minimize the number of worker hours. So in this case, we're maximizing the profits, and so then we look in the problem and what kind of numbers deal with profit? Well, that would be our money. So our $35 for each bowl and our $30 for each plate. So our profit function is going to be 35, the price, times the number, x is the number of bowls, plus 30 is the price times the number of plates, which is y. And so now we're going to set that aside for a minute until we can get our feasible region determined. We're going to determine those from the constraints. And very often the easiest way to determine the constraints is let's first organize our information. So again, we're dealing with the number of bowls and plates. So we're going to organize our numbers into which numbers deal with bowls and which numbers deal with plates. Well, if we start at the very beginning of the problem, bowls take 5 pounds of clay. Plates take 4 pounds of clay. The potter wants to make at least 4 bowls, so that deals with just our bowls. And the only other number given in this problem is 40 pounds of clay total. So that 40 pounds of clay has nothing to do specifically with just bowls or plates. So that's why we're kind of putting it under both of those columns. And so now what should our constraints be? Well, 5 pounds of clay, 40 pounds of clay, or 4 pounds of clay, and 40 pounds of clay total should tell you that one of your constraints is 5 pounds of clay times the number of bowls plus 4 pounds of clay times the number of plates, has to be less than or equal to the amount of clay we have. And so that will be our first inequality. The second inequality, we need to have at least 4 bowls, so we can have more than 4 bowls. So x has to be greater than or equal to 4. And then, of course, we can't have a negative number of plates, so y has to be greater than or equal to 0. Solving the first equation for y, we get y is less than or equal to negative 5/4 x plus 10. That, along with y is greater than 0 and x is greater than 4, should be our 3 regions. So let's go ahead and graph those lines. Go ahead and pause the video and try to do that. So there's the line y is less than or equal to negative 5/4 x plus 10. And now we need to graph x is greater than or equal to 4, so that's going to be a vertical line. And then y is greater than or equal to 0. And again, we need to determine the feasible region. What is the bounded region that we have? Where do all those inequalities overlap? And again, it's this orange region. So our vertices are going to be 4, 0, 8, 0, and 4, 5. And when we go ahead and plug each of those into our objective function, if we were to sell 4 bowls and 0 plates, we would have a profit of $140. 8 bowls and 0 plates would give us a profit of $280. And 4 bowls and 5 plates will give us a profit of $290. So if we want to maximize our profit, we're going to have a maximum profit of $290 with 4 bowls and 5 plates. So again, this is a word problem. Please make sure that you are answering your question in a sentence with words. I'd like you to try the next problem in your note packet, at least try to set it up. It's another linear programming word problem. We will be going over it tomorrow in class, but I want to see where you're at with it. You will be having a project dealing with these problems, so I'd like to see what you can do, and the easier you can do these, the easier this little project is going to be. So please make sure you come to class with questions, anything on these last 3 problems that we've done that you don't understand. Or, if you have no questions, I will assume that your next problem is completed and hopefully right. And again, as a reminder, please make sure you go back and do the notes check. And we'll see you in class tomorrow.